Today we're going to be proving Euler's Totient Theorem. It says that if you have two positive integers n and a, and phi is the totient function, I'll explain what that means later, then n and a are coprime to each other, I'll explain what that means too, if and only if this congruence holds. Now, fun fact, Euler only proved the forwards direction of this theorem, but it's actually an if and only if. So today we're even going to prove a stronger statement. But first, I got to explain a few things. First of all, what does the word coprime mean? It's a definition. Two integers a and b are said to be coprime to each other if they have no prime factors in common. So for example, 6 and 25 are coprime to each other because the prime factors of 6 are 2 and 3, and the prime factors of 25 are 5, and well, just 5, but it appears twice in the prime factorization. But notice these have nothing in common, so therefore they're coprime. However, 6 and 14 are not coprime to each other. Why not? Because the prime factors of 6 are 2 and 3. The prime factors of 14 are 2 and 7. And look, they both have a 2 in common in their prime factorization. So they're not coprime. Finally, the number 1 is coprime to anything, even to itself, which might surprise you. But the reason is because you prime factorize 1, well, it has no prime factors at all, so it doesn't have prime factors in common with anything. What is the totient function, phi? Well, it's a function which takes a positive integer n as input, and its answer is a positive integer, and it tells you how many integers are between 1 and n inclusive, which are coprime to n. So for example, let's say we want to compute phi of 9. This is the number of integers which are coprime to 9. So, okay, let's list them out. Well, 1 is coprime to 9 because 1 has no prime factors at all. Remember, 1's coprime to anything. 2's coprime to 9 because, okay, the only prime factors of 9 are 3 and 3, so this doesn't have a 3 in it. However, 3 is not coprime to 9 because it has a 3 in it. However, 4 is coprime to 9 because prime factors are 2 and 2. 5's coprime to 9. 6 is not coprime to 9 because they both have a 3 in it. But 7's coprime to 9, so is 8. And what about 9? Well, 9's not coprime to 9 either because they both have a 3 in it. So here are the numbers which are coprime to 9. And so therefore, phi of 9 is just how many of these guys there are. It looks like there's 6 of them. So phi of 9 is going to be 6. Okay? Finally, this notation here, which just means A is congruent to B mod n, that's just the same as saying that when you subtract these two guys, their difference is divisible by n. For example, 72 is congruent to 12 modulo 10. Why? Because if you subtract them, what do you get? You get 60, which is a multiple of 10. Okay, so let's prove this. We're going to prove the forward direction first. So assume n and a are coprime. And what do we want to show? We want to show that this guy is true. How do we do it? Well, there's a trick we can use. However, for the trick to work, I don't want to have to think about the case when n equals 1 because that's weird. However, notice that if n is 1, then this is true automatically. Okay, well, notice that in the special case that n is 1, this congruence holds. And why? Because saying that this is true is the same as saying that when you subtract these two guys, the result is divisible by 1, okay? The thing is, any integer is divisible by 1, so this is trivially true. Assume then for the rest of the proof, at least proving the forward direction, that n's not equal to 1. So that means it has to be 2 or greater. Let S be the set of integers between 1 and n inclusive, which are coprime to n. How many elements is this guy going to have? Well, it's going to have phi of n, of course, because remember, phi of n just means how many elements between 1 and n are coprime to n. So let's list them out. We can write S in the form x1, x2, dot, 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 all the way to how many elements? X phi of n. So there's phi of n elements in all, where let's say x1 is less than or equal to x2, etc. So we list them in increasing order from least to greatest. So these are all the numbers between 1 and n, which are coprime to n. Let T be this set. The set obtained by taking each of these guys, multiplying it by A, and then whatever number you get for that, reduce the result modulo n. By the way, notice this mod n doesn't have parentheses around it, unlike this kind. That's because they're two slightly different concepts. This notation, x1 mod n without parentheses, this means what's the unique number between 0 and n minus 1, which is congruent to ax1 modulo n. For example, if you want to compute 72 mod 60, that's just 12. Why? Because 12 and 72 are congruent to each other, modulo 60, and 12 is between 0 and 59. So there's infinitely many things which are congruent to this guy, mod 60. But when you write it without parentheses, that means what's the unique answer that's between 0 and 59, okay? Now here's where the magic happens. It turns out that these two sets are actually equal. They have the exact same elements. Let me show you an example of that. For instance, consider the special case that A equals 2 and N equals 9. Okay, in that case, what's S? Well, S is the set of numbers between 1 and 9, which are coprime to 9. So as we saw earlier, that's going to be 1, 2, 4, 5, 7, and 8, okay? Now to compute T, well, what we got to do is we got to take each of these numbers, multiply it by A, and then reduce the result mod N, or in this case, mod 9. Okay, so take our first guy, 1, multiply that by A, you get 2, and 2, if you reduce that mod 9, well, it's already reduced, so you just get 2. Okay, same thing here, 2 times A, 2 times 2, that's 4, reduce that mod 9, it's still 4. Okay, for this guy, 4 times 2, we get 8. Reduce that mod 9, we still get 8. 5 times 2, you get 10, but that's not reduced. But when you reduce it mod 9, you get 1. 7 times 2 is 14. Reduce that mod 9, you get 5. 8 times 2 is 16. Reduce that mod 9, you get 7. And notice these two sets are equal. They have the same exact elements, even though they're written in a different order. It turns out that's not a coincidence. Let's try to prove that that happens in general. You want to show S equals T. How do we do it? Well, first of all, observe that the number of elements in T can't be more than the number of elements in S, right? Because you obtain the elements of T by taking each of these guys, there's phi of n of them, multiplying by A and reducing the result mod n, okay? So you can't get more things than you originally have in S. However, at least hypothetically, it seems possible that you might have less elements in here, because what if a couple of them happen to be equal? Okay, we know that all the guys in S are distinct because we listed them from least to greatest. But how do we know that these guys are distinct? It turns out they are, but it's not obvious. It's something we got to prove. So here's a claim. If I is less than J, then these guys are not equal. Okay? If we can prove this, this will show that all these guys are distinct from one another. We're going to try a proof by contradiction. So towards a contradiction, assume we have some combination of I and J such that I is less than J, but that these guys actually are equal. Okay, well, here's the thing. We know that AXI is congruent to AXI mod n, modulo n. Why is that? Because this guy is the unique thing that's congruent to this guy, just between 0 and n minus 1. And by similar logic, we know that AXJ has to be congruent to AXJ mod n, modulo n. But here's the thing, these two guys, we assume that they're the same. So since these guys are the same, that means these guys have to be congruent to each other. So therefore, these two guys have to be congruent to each other. One of the basic properties of modular arithmetic is transitivity. So if A is congruent to B and B is congruent to C, then A has to be congruent to C. Okay, so that means these guys are congruent modulo n. Now, what does that mean? That means when you subtract them, the difference has to be divisible by n. And by the way, it doesn't matter what order you subtract these two guys, because whether or not it's divisible by n, well, if you subtract them in a different order, you just get a negative, so it doesn't affect divisibility in any way. We know this is a positive number because a is positive, and then xj is bigger than xi. And now we can simplify this a little bit. We can factor out an a from this guy. Okay, well, now here's the thing. Since a and n are coprime, that means a and n have no prime factors in common at all, right? So that means since this whole thing's divisible by n, then that means all the prime factors that appear in the prime factorization of n also have to appear in the prime factorization of this guy. So that means this part is divisible by n. So therefore, this guy has to be divisible by n. Okay, but now here's the problem. Recall that these xj and xi, both of these guys have to be between 1 and n inclusive, right? So at most can be n, at least it can be 1. But here's the thing. Okay, this always has to be strictly less than n, because the biggest this thing could be is n minus 1, right? If the first guy's n and the second guy's 1, that's the biggest it could be. Okay, but then we also know that this can't be 0, because if it was 0, xj and xi would have to be equal. Okay, in fact, this always has to be positive since xj is bigger than xi. So this whole thing has to be bigger than 0, but less than n. So there's no comprendo way this could be divisible by n. So that's a contradiction. Okay? So that means our assumption was wrong. So therefore, this is true. Whenever I is less than j, these guys are not equal to each other. Okay, so this claim is important because it shows that all of the guys in this set that we listed here are distinct. None of them are equal to each other. So what does that tell us? That tells us that T has exactly phi of n elements. So in particular, T and S actually have the same number of elements now we know, which is stronger than what we said earlier. So we know now that the cardinality or size of T is exactly phi of n. In other words, T and S have the same size. Now, this is important in showing that S and T are equal. To show that S and T are equal to each other, it suffices just to show that T is a subset of S. This notation means that everything in T is also a member of S, okay? Because if you have two finite sets which of the same size, then there's a theorem of set theory that says they're equal if and only if one's a subset of the other. That's why it was really important to show this. So we want to show each element of T is also an element of S. Since the elements of T are of this form, it suffices to show that each of these guys is an element of S. But what are the elements of S? If you recall what S is, it's the set of numbers between 1 and n, which are coprime to n. So therefore, to show S equals T, it suffices to show that for each of these guys, that it's between two things, that it's between 1 and n, and that it's coprime to n. Okay, so how can we show both of these things? Well, let's try to show this first. Okay, now here's the thing. When you do something mod n, remember, you get an answer that's between 0 and n minus 1. So we already know that this guy's between 0 and n minus 1. So to show that it's between 1 and n, it just suffices to show that this is not 0. So I claim that this guy is not zero. And why is it not zero? Well, towards a contradiction, assume that it is zero. Assume AXI mod n equals zero, okay? Well, if this equals zero, then in particular, that means when you take AXI, it turns out then that AXI has to be congruent to zero modulo n, right? Because we know this is congruent to this, and this equals zero, so therefore it's congruent to zero, okay? But remember, congruent mod n, that just means when you subtract these two guys, your answer is divisible by n. So in particular, that means AXI minus zero, which is just AXI, is divisible by n. But this is impossible. Why? Because a is coprime to n, so it has no prime factors in common with n. And xi is, remember, xi is an element of S, so it's coprime to n. So both of these guys have no factors in common with n except for one, but no prime factors, I mean. So therefore, when you multiply them together, their product also has no prime factors in common with n. So there's no comprendo way that this could be divisible by n, so that's a contradiction. And now here's a subtle point though, is if n was 1, then there would be no contradiction. This would be true because anything is divisible by 1. But so remember, we are assuming earlier, we assumed earlier for the rest of our proof of the forward direction that n's not equal to 1. This is why, okay? Because otherwise the step of the proof would be invalid. Okay, so assuming that this guy equals 0 leads to a contradiction. Therefore, the assumption was wrong. So this must be non-zero after all. And since we know that AXI mod n, well, anything mod n has to be between 0 and n minus 1, we know that since it can't be 0, it has to be between 1 and n minus 1. If it's between 1 and n minus 1, then in particular, it has to be in this set, which we wanted to show. All right, so we showed that this is true. Now, can we show that this is true? Let's do that in another claim. I claim that this is true, that AXI mod n is coprime to n. Towards a contradiction, assume it's not coprime to n. Well, if it's not coprime to n, that's the same as saying this has a prime factor in common with n. So towards a contradiction, assume that P is a prime factor common to both this guy and to n, to both AXI mod n and to n, okay? If they're not coprime, then they have a prime factor in common. But now here's the thing. Remember, AXI has to be congruent to AXI mod n. Of course, congruent modulo n, right? But what's this the same as? This is the same as saying that when you subtract these guys, and it doesn't matter if this is positive or negative, when you subtract them, this is divisible by this, by n. So since this guy's divisible by n, we can write this guy as k times n for some integer k. So write this as k times n for some k in z. Z is the set of integers. And now here's the thing. If we rearrange and do some algebra, move this to the other side, we get AXI equals KN plus AXI mod n. Okay. And now here's the thing. Since P is a prime factor of both this and n, well, that means since this guy is divisible by P, this guy has to be divisible by P. And then likewise, this guy is divisible by P. So when you add two numbers that are divisible by P, then that means the whole thing has to be divisible by P, okay? And since this is equal to AXI, that means AXI has to be divisible by P. This is impossible because since A and XI are both coprime to n, they can't have any prime factors in common with n. But P is a prime factor, which appears in the prime factorization of n. So therefore, a times xi is going to have a p in its prime factorization. Well, we said that it does, right? But theoretically, it shouldn't, because neither a nor xi has a p in it. So this is a contradiction. So that proves that there's no way that there can be a prime factor common to both of these guys. So therefore, the only conclusion is both of these guys have to be coprime to each other. Okay, so that proves the claim. Okay, so we proved that this is true, right? That was what we proved in this claim. And earlier we said that this is true. So since both of these things are true, that means S has to equal T. So we've proven that S equals T, which is probably the most important part of the proof. So that means these two sets are equal. Now the numbers may be written in a different order, but we know that the two sets contain precisely the same numbers. In particular, if you multiply all these numbers out, the product should be the same. So that means if you do x1 times x2 times ... times x phi of n, that's equal to multiplying all these guys out. Now here's the thing. When you take this product of all these guys, it turns out that the product is going to, of the individual things, is going to be the product of just ax1, ax2, ... So since each of these guys is congruent to one of these guys, the product is congruent, okay? And why is that? Well, there's a little fact of modular arithmetic we can use that says if A is congruent to B and C is congruent to D, then A times C is congruent to B times D. But let's prove this in case you don't know it. Okay, since A is congruent to B, we can write A minus B in the form K times N for some integer K. And likewise, since C is congruent to D, we know that C minus D is some multiple of N. Let's just say it's M times N. So now what about this guy? Well, if you do AC minus BD, what's that the same as? Well, we can rewrite this as AC minus AD plus AD minus BD. And why am I doing that? Because then you can factor some stuff out. You can rewrite this as A times parentheses C minus D plus factor out D out of this part. We get this, okay? But what's this? Well, the C minus D part is just M times N. And this A minus B part is just K times N. And so it's easy to see that this whole thing here is a multiple of n. So that means this guy is divisible by n. So therefore, these guys have to be congruent mod n. Okay, so that means if you multiply any two guys in this thing, their product should be congruent. This guy is congruent to this guy is congruent to this, etc. And even though we're multiplying more than two things here, potentially, well, we can just keep applying this multiplication lemma as many times as we need until we get that these whole products are congruent. Okay? But now, okay, this guy on the left, what's this the same as? Well, this is equal to the product of the x's. And now here's the thing. We would like to cancel out these x's. How is there a way we can do it? Well, since we know that these are congruent mod n, this is divisible by n. Okay, and now we can rewrite these. Notice we have a times a times a. We have a bunch of a's in this product. Well, how many a's are there? There's actually phi of n a's. So a times itself, phi of n times is just an exponent, a to the power of phi of n. So you can rewrite this as x1 times ... times x of phi of n as one thing. Parentheses, the other thing is going to be a to the phi of n minus 1, okay? These are the same as this by the distributive law. But now here's the thing. Since n is an integer that's bigger than 1, and each of these guys has no prime factors in common with n, then that means all the prime factors that appear in the prime factorization of n are going to have to appear in this guy. So that means that this guy is going to have to be divisible by n. And what does that mean? That means a to the phi of n is congruent to 1 modulo n, which is what we wanted to show. If n and a are coprime, then this congruent holds. So we proved that forward direction of the proof, that this implies this. Now let's prove the backwards direction. For the backwards direction, we want to assume that this congruence holds, and we're trying to show that n and a have to be coprime to each other. How do we do it? One way is by contradiction. So towards a contradiction, assume that they're not coprime. Okay, if they're not coprime, that's the same as saying they have some prime factor in common. Assume P is a prime factor, which is common to both of these guys. Okay, well, here's the thing. Since we know that this is congruent, what we can do is we can rewrite a to the phi of n minus 1. We know this is divisible by n, so we can write this in the form k times n. And now if we do a little bit of algebra with this, we can rewrite this as a to the power of phi of n minus k of n equals 1, right? But now here's the thing. This guy right here, this a to the power of phi of n, this has to be divisible by p. And why is that true? Well, we assume that p is a prime factor of a, right? Now, you might think, well, what if this is to the a to the power of 0? But the thing is, phi of n can never be 0. It always has to be at least 1. The reason for that is because the numbers between 1 and n, which are coprime to n, well, there's always at least one number that works because 1 is coprime to anything. So therefore, this isn't a to the power of 0. This is a to the power of 1 or 2 or 3 or some positive number. So therefore, since a is divisible by p, this whole power has to be divisible by p. Okay, and then since we said that p is also a prime factor of n, that means this part right here is also divisible by p. But now when you subtract two things that are divisible by p, you should get an answer that's divisible by p. So therefore, this 1 here is divisible by p. And that's a contradiction because 1 can never be divisible by a prime number p. So our assumption that there was a prime factor common to both must have been wrong. Therefore, these must have been coprime. So that finishes the proof. So we showed that n and a are coprime if and only if this is true.